In this video, we'll look at implementing the Newton-Raphson algorithm for a system of equations with finite difference approximations in the Jacobian matrix. After studying this video, you should basically be able to do what I just said. So let's look at an example. So we'll solve this system of equations. Here we have a three variable system. Lots of nonlinear things going on here with the sine, the y squared, the natural log, z cubed, 2 to the y. So lots of nonlinearity in this system. It would be relatively tedious to calculate all of these partial derivatives. So we'll look at how we can do this with finite difference approximations. So again, here is the main M file to call Newton-Raphson. And included here is our anonymous function to calculate the function evaluations at each iteration and our initial guesses of 1, 1, 1. And then the Jacobian is defined in an external file. Just a reminder that that @ sign there is because this is in an external function M file. And let's take a look at what that function M file looks like. So first, it looks like a lot of typing, but you might realize pretty quickly that you can do a lot of this with cut and paste. So here we have, I've just defined anonymous functions, and I did them here in terms of x, y, and z, just because it made it easier to think through the partial derivatives. But I've defined one for each function, each of the equations. And here's our del, that's the amount that we're going to perturb, we'll say, each function to estimate its partial derivative. So then we just go through. So in this first equation, you'll see right here, we will perturb the first variable, x1, in this case that's x, and then divide by that. And in the second one, we'll df1 dx2, we're going to perturb x2, divide by del times x2. And in the third one, we're going to add a little bit to x3. That's all I mean when I say perturb. We're just going to add a small amount to x3, divide by x3. And so if you can see a pattern here. In the second 3, we're going to be working with the second equation, and the last ones will work in the last equation. And then the last thing to do is just to put these results in matrix form. Always remember that form of the Jacobian matrix where each column is all of the partial derivatives with respect to one of the variables, so in this case x1. So x1 is the first element in the first column, second element in the first column, third element in the first column, and each row corresponds to one of the equations in the system. So df1 in the first row, and df2 in the second row, and df3 in the third row. And so that builds the Jacobian. So we can go back here, call this function, and see what we get. So I've actually included 2 outputs here. The first is for our initial guesses of 1, 1, and 1, and we see that Newton-Raphson solves the system. It's about 0.6, 2.4, and 2. Very small residuals again. Approximate relative error on the order of 10 to the minus 10, also very good. And quick convergence. 6 iterations. I've also included a second case, and I'd encourage you to play with more cases and see what you find. But in this case, I used 10, 10, and 10 as the initial guesses. And the one thing that's kind of interesting here, you'll notice, is we got some imaginary numbers that showed up somewhere in the calculation. And this is one nice thing about MATLAB, because it can handle imaginary numbers. And to get a sense of where that might happen in the iteration, if you go back and look at the original system of equations, we have a natural log of z. So in a case where z is less than 0, that's where we might get some imaginary numbers. But no big deal. MATLAB keeps chugging along. We do have imaginary components to our residual and our approximate relative error values, but that's all very small numbers, and we did eventually converge on the same solution to the system of equations. Though one thing to note is because the initial guesses were farther away from the value, the convergence was a little slower. Still, 10 iterations is plenty satisfactory. So I'd encourage you to play with this example and maybe try some different initial guesses and see what else you can discover.